Howdy folks, welcome back to CS 128 Honors. Today we're going to be talking about generics and smart pointers in Rust, two extremely powerful features of the language. So a couple goals for today. We're going to answer one brief question from your Prairie Learn submissions, probably clarify something with ownership and borrowing. Then we're going to briefly review struct methods from the last two lectures, and then finally introduce generics and smart pointers. And at the end, I will be going over homework 8, giving you guys some hints, helping you get started. Just a quick warning, this homework is very hard, so I strongly recommend you watch this lecture before attempting it. And of course, use the hints at the end of the lecture. Okay, let's get into things. So, a couple quick reminders. Homework 7 is due next week on Tuesday at midnight. Homework 8 will be releasing tonight. It'll be due on the 6th at midnight. And then MP2 is releasing tonight as well. It's going to be due next Friday at midnight. Okay, so let's get into the question. So does a string slice of word mean the same thing as a string slice of dereferenced word, given that word is a string? So not quite. If word is a string, you can't dereference it. Dereferencing is not supported the same way it is in C++ or some other language. When you have some type of string slice, that's all it is. You can't really dereference the string, so this little bit in Rust would not compile. On the other hand, so when you have this syntax, ampersand, word, and then slice, this means take a substring of word that covers the entire string. So once again, ampersand borrows the original word, and then the bracket notation defines where to start and end the substring. So you cannot dereference word if word is simply a string. You can only dereference word if word is a mutable reference to a string. So slight distinction there. We'll be going over more about dereferencing in today's lecture. Okay, on to reviewing structs. So struct methods are very, very similar to functions you've seen in previous lectures. Use the fn keyword to define them. Struct methods contain code that is run somewhere else, so they're just like any other function. But they're defined in the context of a struct. So when you define this struct method, you're given this instance of a struct that you can operate on. So you'll use the impl keyword to implement the custom methods for your type. This impl block is sort of your method definition area. And as always, the first parameter of these struct methods are always self. They represent the current instance of the struct method, or the current instance of the struct that the method is being called upon. And so you can have various versions of self, a immutable bar to self, a mutable bar to self. You will almost never see self by itself, simply because when you call a method on a struct, you don't want to consume it. There are patterns in which self is used, like a builder pattern, or something like an into iter, where you're consuming the struct. But in this class, you'll almost always use ampersand or ampersand mute. Okay. And then once again, like I said, you can immutably borrow self for the current instance of the struct, mutably borrow the current instance, and you'll use dot notation on self to access the struct fields and call other struct methods within any other method. Okay, with that out of the way, on to generics. So generics are this powerful language feature that allow you to generalize types to broader cases. Take something like a vector. Rather than just having a vector class be a vector of ints, or defining a new class for a vector of strings, we have vector as this container that can take any type. You can make a vector of anything. And that is due to generics. Generics allow you to create some type of generic container or generic class, and you can fill in whatever type goes into that class. So they help in reducing code duplication. So like I said, rather than creating a class for a vector of strings and a class, or rather a struct for a vector of ints and a struct for a vector of your custom struct, you have one singular vector type, and you can modify that type by plugging in a different subtype. So you can just plug in a vector of strings, plug in that string into the construction, and you'll get a different type of vector. So you've seen this before. They're usually represented with this little bracket notation, angle brackets, and some type t within it. And so this notation describes one or more generic type parameters. So if you see a single t or a single type within brackets, that just means that your container takes a single type. You can see multiple, so take the result type. You have two little types within your brackets. And the next slide will show you some examples. Okay, so I want to make a quick distinction. You have two different types of types in Rust. You have the concrete types, so types that do not take a generic, and generic types. So concrete types are your usual int, string, something that does not have these angle brackets. And generic types do take these angle brackets. And so you've seen these before. You have option t, an optional element of type t. So you can plug in anything here. You can have an optional string, an optional integer, and we'll see in homework 8, an optional link for your linked lists. And like I said, with result, you can have multiple types within your brackets. So the result is some success with type t or some error with type e. So you put these two different types in these angle brackets. And like I mentioned, you can have a vector of type t. You only need to define one single class, your vector, and you can construct a vector of any type once you've defined it. So generics allow you to have this repeatable use cases without repeating your definition code. And you'll see hash sets in MP2 and hash maps in MP3. So we'll be going over how to use these in future videos, but keep in mind, generics are all over the place. You've used them before, you'll continue to use them as you code in Rust. So they're extremely powerful. Okay, so how do we define generics in Rust? Well, generics are essentially templated custom types. So you'll define a generic using a struct or an enum. Structs like a vector, or enums like an option. You can also have templated functions. You'll see this in the case of something like the collect function or the from string function, as you saw in, or rather parse in MP1. You can convert a string into any type, and so you only define one sort of templated function called parse, and Rust will handle, parsing it to a usize, parsing it to an I32, whatever it may be. Templated functions are somewhat out of the scope of this class. We'll only be showing how to define custom types, but they are something that is part of the language. You can also have templated interfaces, traits. These are also way outside the scope of this lesson, but we may cover them in the special topic sections when you guys begin completing final projects. Okay, so let's see how to write some generic code. If I have this little dummy data class here, that's value, and it contains an F64, and I can, get some data out of my value, and I want to turn this into a generic, I need to use that angle bracket notation that we've seen before. And I want the underlying data to be generic. So I have some outside wrapper struct, and the inside data is generic. So I can use angle brackets to define that. So it's the same notation, struct, generic val, name of the struct, but at the end I have this angle brackets with t in the middle. T is any type. The user of my new struct can plug in anything for these angle brackets, and genval will have that type t. And then the other new little syntax is when you're writing the implementation for your new type, you put a angle bracket t after both the impl and the struct type. So you're saying you're implementing methods for any type t on a generic struct of any type t. You can get more specific when you have very specific use cases of, say, like vector of booleans. You can implement a custom implementation for some type t, but usually you'll stick to a generic implementation for any generic struct. So impl t and generic value t. And we can use this type t as a sort of placeholder. When this code is compiled, this will sort of get copy and pasted out. So if I have a generic value of string will get copy pasted in place for t. If I have a generic value for usize will get copy pasted for t. And so you can sort of use this as a cutting down on boilerplate if you have multiple containers and you're going to put different types inside your containers. Okay, let me move my camera out of the way briefly. So how do we use this? Well, if we're going to define our original struct value, well, we just simply say some variable val is a value that has type 3 in F64. To define our generic structs, we can do this a couple of ways. So if we want the compiler to know what type is going to be in there, we have to specify that type with the colon notation and the new type. So we have generic value, and in angle brackets, we put the type we want to contain inside of our generic value. So generic value of I32, and we define a struct and pass it an I32 there. We do the same thing with strings. We have a generic value, and we're putting a string in there. And same thing goes with F64. In some cases, Rust is able to infer the generic type that you're putting in there, but it is best practice to sort of state that you have a struct of some generic type. It'll make reading your code easier. It'll make your life a lot easier when debugging compile time errors. So best practice, always try and put whatever type you're using when you're using generics. Okay. So we mentioned that option is a generic. So let's see if we can implement a custom option type. Okay. So like I mentioned, we can define a custom generic using this angle bracket notation. And one thing to note is you can also have generic enums. So remember, enums can contain a type within them. And so we're saying our enum can perhaps contain some type t in this some variant, or not contain a t in our none variant, the same way an option does. Okay. And when we want to implement some methods on it, we have this impl bracket t on my option t. So you're probably familiar with the unwrap method. Strongly recommend against it, but we can go about implementing it. So if I have a enum, I can match myself. So I'm going to match self and cover the two cases that it can be. Sum and some value of type t. So my sum, and then my none case where there's nothing inside. And so when you're defining a custom enum, you almost always have to preface the types with the type it is, unless you use some custom module import statements. We'll cover those by the time final project rolls around. But as always, when you're defining enums or using enum variants, you got to put the type in front with double brackets. Okay. And so if we have some value, we're going to return b, which is val, which is a reference to whatever t is in here, because we're taking a borrow of self, and so we get a borrow of the value inside. And if there's nothing in there, well, we'll panic. Our code will crash and burn, the program will stop, so we almost always want to never call unwrap on a none value. Okay, so now is sum. So this will be somewhat similar. We will match self and return a boolean based on what type we see in there. So self, and we don't care what's inside, we just care if it's a sum, so we can use this wildcard bracket, or wildcard match. So if we see a sum, we return true. If we see none, we can return false. And as far as implementing is none, well, that's just the opposite of is sum. So we can Boolean negate that and Boolean negate the value that's returned by this is sum function. Okay, so let's briefly go over this example. So we're defining a custom enum, my option, that has an optional string inside. And so we have the sum variant, we put a string inside, and we can call the isSum method on that, and then unwrap to get the value inside. And we can also define a none option and use the isNone method. And so at the very end, our code will panic because we're trying to unwrap that. Okay. Messed up my terminal. Okay, so I had some invalid cargo configurations. So I fixed that by renaming my file to my option. Cargo a bit confused with the command line arguments. So I can run this with cargo run, the binary my option, and there we go. So at the very beginning, we find a optional string inside the my option, print that out. Then next, we define a new option of a potential unsigned 8-bit integer, and we found an empty value since is none returned true. And we know we're going to panic, and we do panic at the very end at the explicit panic. And Rust gives us a backtrace that says we panicked at this line 11 here. Okay. On to the next topic, so smart pointers. You'll often see smart pointers paired with generics, especially when you have some type of custom data structure. And you'll see these extremely heavily used when you're using generics and traits. So if we end up covering smart pointers and traits in the advanced topics lectures, you will see boxes and smart pointers a lot. So in general, pointers are these concepts for variables that contain an address to some place in memory. And smart pointers are these advanced data structures that not only act like a pointer, but also have some additional metadata and capabilities. So what do we mean by this? Well, you've seen these before. String and vector are smart pointers. They manage their own memory. They are pointers to some place in this heap. They manage their own memory. They do some internal bookkeeping. Will allocate more memory for you if you add to the vector or you add some characters to your string. And they have some metadata that like the string length, the vector length, any type of additional information there. And the important thing is smart pointers take ownership of the data they point to. So you've seen these with vectors. You're not able to sort of move out of a vector. You always have to borrow because vectors have ownership of the data it points to. They have ownership of every value inside. And so when the smart pointer structure goes out of scope, the data it owns is also dropped due to the rules of ownership. So the owner of the data inside is the vector, and once the vector goes out of scope, all of that data is dropped. So smart pointers are just this generic data structure that act as pointers and have some additional capability. That's the big takeaway. So we'll be using the box smart pointer when you're implementing linked lists in homework 8. So boxes allow you to store data on the heap rather than the stack. So this can be extremely powerful if you don't know the exact size of the data and when putting it on the stack. So the pointer to the heap data is on the stack, your box is on the stack, but the data inside the box is on the heap. And so when the pointer on the stack, when your box goes out of scope, the data that it points to is freed. So this is extremely powerful because it will manage the memory inside of it for you. The box is this smart pointer that has some pointer to some data, and it has these additional capabilities to free that data for you. So all this talk about the stack and heap, what does that mean? Well, if we have this little box here, a simple struct, and it has a pointer to some heap data. So our box itself is on the stack. The owner of this heap data, it points to this data. The data is on the heap. We don't care about it. The box owns that data, and so the box will manage whenever we want to free or access that data. So whenever you want to interact with this data, you're interacting with the box, and the box will handle the interaction for you. Okay, so how do we use them? Well, first, you're going to order some cardboard boxes from somewhere like Amazon, maybe some shipping container boxes if you're moving out of an office. No? Okay. So you'll create a box smart pointer using the box new syntax. And so you'll make the box variable mutable if you want to be able to modify the data that it points to. So the box owns the data, so you got to make it mutable for it to mutate itself, mutate the data that it contains. And so you'll dereference this box smart pointer to get access at the data it points to, similar to something like C++ and smart pointers there. However, if you're calling a function on the data, you do not need to dereference that box. Rust will do it for you. Okay, let's see this in action. So I have my new box here. It's a box of string. And the big thing to note is the box type itself is generic. It is some smart pointer that contains a generic type. In this case, it contains a string. So we create a new box with box new. We pass in the value that we want it to point to, this new string, and we can print it out. And like I pointed out, when we want to append some text to the data inside our box, we do not need to dereference it. Rust will do that for you. But when we want to explicitly modify that data, the data inside, we want to change what that box points to, we have to dereference our box. So if we want to simply modify this data inside and call a method on it, we can do that. Dereferencing is automatic. When there's no methods being called, we have to dereference. So if we run this, we see we first print out CS128 honors, then CS128 honors is the best, and finally we change our data and print out hello there. Okay. So when do we use boxes? We'll use boxes when we have some type that cannot be known, whose size cannot be known at compile time. So what exactly does this mean? Well, if we have some type of recursive type, a type within a type, say a linked list, you can use a box to, wrap around that and give you an exact compile time size. We'll show you an error in just a little bit that points out what exactly this means. So you'll also use boxes when you want to own some type of value that implements a particular trait rather than being of a specific type. This is, again, part of the advanced topics lectures that we will be covering during final projects. So don't worry too much about this yet. Okay. So let's say we go back to our linked list implementation. Linked lists are of this form. They have some head pointer at the front of our linked list, and then we have some data inside, and then a pointer to the next element. And we have data inside our link, and then a pointer to the next element. And so we could implement this with this little struct in Rust. We have our link that has some data of type T, and an optional next link. So in case we're the end, we can point to none. If we're in the middle, we can point to some data. Well, there's an error with this. Rust does not like the fact that this is infinite. So if we take a look at this diagram here, our outer link, it's some link with some data T and a pointer to some next link. And that pointer to some next link also has some data T and another pointer to some next link. And we keep going, and infinitely until, well, forever. Rust is not able to create a type when it does not know the size. It does not know when this infinite sort of recursion will end. So we use a box to fix that. And the Rust compiler will even tell you to use a box. We can't use this link inside a link without having a box there. So we can fix this by simply adding a box around our link in order for this to compile. And it's the same thing. We have some data and then a smart pointer to the next data. And some more data and a smart pointer to the next link. So boxes allow you to sort of have a value of fixed size on your stack when you're instantiating generic types and recursive types. Okay, so this is the end of the new content. This lecture might go a little bit long because it gives you a massive head start on homework 8. So I strongly recommend you watch this a little bit, but this is the end of the current lecture 10. Okay. So in homework 8, you will be implementing a linked list. We will give you these struct definitions. So you have your front pointer, which is an optional boxed link, and your link definition, which is an optional boxed link, like we showed you in the previous slides. And you'll be implementing all of these functions for our linked list. So I want to talk about add front and add back because these are very tricky. The rest of the functions should be fairly straightforward once you've seen how to implement add front and add back. Okay, so I've written out a couple sort of pseudocode ideas of what we want to do within our methods. So for add front, we create some new link to contain thing, our new piece of data. Then we're going to update the head pointer, what our linked list points to, update front. And then update some list metadata. So the size, just the size. Okay, let's get started with this. So let's create our new link. So let our mutable link, it's a boxed link t. And so we create a new box with box new, and you will be implementing this link new method. So we can use that here, link new, and the constructor takes a thing which is some type t. Okay. And so we've created our new link. We have our data initialized, but we want to say that this current link points to the original front of my linked list. So there's this method that allows you to sort of take ownership from your linked list and say that link's new element is the original first link. So we can say that with link.next equals self, so the linked list's front, and we're going to take it. So we're going to take the sum that's from here and replace it with a none. So front at this point is now none, and link's next is now this value here. So take ownership of front from the vector or from the linked list and give ownership to the link's next. So we took ownership of that. This front is now none, so we want to reset that. The new front is this current link. So self.front. And then finally, we can update the metadata. Incremented by 1 since we added a singular element. Okay, so this should be a pretty good implementation of add front. Let's move on to add back. So add back is a little bit trickier. So we want to iterate through our list until we're at the last link. And so if the list is empty, we're not able to iterate through it, we're going to create the first link. If our list is not empty, we add a link that points to the next link. And then, of course, we update our list metadata. So we'll do that there and get that out of the way. Okay. So how do we iterate through a list using optional boxes of links? This is a bit tricky. So I'm going to create a variable to keep track of where I am in the list. And we're going to want to change that, so we want to make it mutable. So our current is a optional boxed link of type T. So not only does it have to be this explicit type, we want to be able to change it because we want to set its new next. So if we're at the last link in our list and we want to change or add some data to it, we want to change this next pointer from none to be some of a new link. So we want to make this a mutable reference. Okay. And so we start at the front element. So current starts at the front. It's a mutable reference to some optional boxed link. And we're going to iterate through our list. So while current is sum. Okay. And let's think about this. If current is sum, we want to be able to get at the next link and also check if it's sum, so we can change current to be the next. So this is where Rust and boxes and options and generics gets very ugly. So asref gets me the data inside the option as a reference. And then we're going to unwrap that to get access to the actual data. So let me quickly show an example of this. So asref converts a reference to an option of a reference to that data. So in essence, what we're doing here is we're getting a reference to the data inside our option by calling asref and unwrap. And we're only able to do this because we know that current is sum. Okay, so we have the data. We want to check if the next is also sum. So if our current is sum and our next is sum, we're going to say current equals the next link. So current is mutable is now equal to a mutable reference to the mutable data of the next link. This is extremely ugly. This Rust code gets very ugly when you're using safe Rust with generics and nested types, which is why you almost never want to implement a linked list in Rust. It's an ongoing joke that linked lists are insanely difficult to implement. So whenever you want to use a linked list in Rust, don't do it from scratch. Use one of the inbuilt types. This is just an exercise for teaching you how to use generics. Okay, last step. If the list is empty, create the first link. If the list is not empty, add a link to the last link. So we can use the length parameter to check if our list is empty. So if self.length okay, so if our list is empty, we want to modify this front pointer. And so create a sum box new link new thing. So we have our option, then the box, then the new link, and we pass in thing to that. Otherwise, we want to change what the current next pointer points to. So same thing, current dot as mute. So same syntax here, and we're gonna say that it points to a new box of, that contains some link. Okay, this is a lot. This should get you started on homework 8. Then the rest of the methods are fairly easy to implement. Let's go ahead and run some quick test cases to make sure this is right. So in our vector, we're going to be adding 2 to the back, then 3 to the back, then 4, then 1 to the beginning, and 5 to the end. So at the end, we should have a vector that says 1, 2, 3, 4, 5. There we go. So we start with an empty vector, add 2, then add 3, then 4, then add 1 at the beginning, and 5 at the end. So this code will be pushed to the GitHub. The GitHub is linked in this video's description. So if you want to use this as a reference when you're completing homework 8, feel free to do so. And good luck. Take care, folks.